Connor.
There they are. Differential equationers.
Hey, good morning, Doug.
That's Raymond is in the house. Hannah is in the house. Get in here.
Jareen is in the house.
Good morning, wife.
Hi,
Good morning.
guys.
Good
Morning, Mrs. Gardner.
Are you learning to love math? Or at least
Yes,
tell it?
ma'am.
Oh, good. Math is actually really fabulous, though I didn't like it in high school. It's my favorite thing, one of my favorites now.
Nerd.
You gotta love it if you're married to Doug, that's for sure.
It was part of our proposal, actually. So, I guess I
Hannah's
knew.
like, what?
Hannah's like, what? Actually, it was after the proposal, Hannah. So I do have a funny story I'm going to tell on him, then I'll go away.
Oh,
you
look
guys
at
can
the
be-
time.
I would love to hear it.
Yeah. So after he proposed, and it was like the next day, and we're sitting on the side of the hill overlooking the coast, and I'm thinking romantic thoughts, right? And he says, how far out there do you think the horizon is?
That's interesting.
And I went,
is that romantic or what?
in my head, I'm thinking, never thought about that. And he's going, let's calculate it. And I won't tell you what I was thinking in my head at that moment. I'm like, seriously? You're going to calculate how far out the horizon is? We're sitting here on this beautiful, and he did. And so, there you have it. I knew what I was getting myself in for. So Hannah, if that ever happens,
Beautiful.
you just keep
know,
that
that's-
thought in your head of, seriously? Okay, let's do that right now. That's what I was thinking about. Have fun.
All right. Now I'm going to crawl out from under the bus and try to recover my self-confidence, teach you guys something.
Oh, way, you should be proud. You grabbed a stick and did it in sand, right?
Exactly.
Like a man.
Exactly. I am proud, actually. That is interesting, and I stand behind my
I thought she made you take a math test before you got married.
right. Exactly. You better at least be able to solve this equation, or I can't even talk to you.
Solution is the date of our wedding and the location. If you want to get there, you have to solve this equation.
Yeah.
What if that was just a polite way of turning people down? It's like, you have to solve this equation, and it's the differential equation with like natural log on the end of it, like we were talking about last class. So we're
Yeah.
just like, I don't know if I can. It's just a polite way of saying no.
Darn, you couldn't do it. Oh, well, shoot. I had such high hopes.
Very educated way of saying no.
Yeah, then you run to that one math grad student.
Oh yeah. Then you just gotta bite the bullet, give them a fake number or something. I don't know.
I don't know if this is I don't know if this is just something all dads do, but wow, that is so tiny. But I was constantly giving my kids like challenges. I considered them to be like confidence builder challenges, because most people are pretty, and you guys will relate to this. We're pretty handicapped by other people's opinions, and so to do something stupid like that requires a lot of self-confidence. And like I had a friend in college who was really an entertainer, and he would like grab his tray of food and then purposely trip in the middle of the cafeteria, and just like all of his dishes go everywhere. And it's like not very many people can do that, like get laughed at and so forth. So I was always trying to get him to do weird stuff, like, run through the supermarket and slide like in baseball. And then I'd pay him, like, I'll get you a Dutch Brothers if you walk up to that person and, ask him some ridiculous question. And anyway,
I don't think my dad tried to get me to do that stuff. I think he would just do that stuff in front of me, and I would get used to it.
It's fun. It's totally fun. I don't care who you are. Okay. No more messing around. Does everything look the same as usual to you? I'm using a different computer. I'm in Idaho, and I didn't bring
Seems
my
normal so
mouse,
far.
and I had to steal my daughter's mouse. Yeah. I'm going to show you something really cool today, and I want to. So this project, pull it up if you haven't already done so. But I think I can also pull it up. Let's see if I can. Should be on Google Drive if I did my job. Yes, it is. And again, I want you to understand this before you're done, and I'm willing to help you until you get it right. I want you to work with another person or even two other people. I want everybody to get 100% on this, but it requires some explanation. And it's, as I said the other day, it's one of my kind of all-time favorite, I don't know, it's one of my favorite defenses of math. I mean, it's complicated enough that I can't explain it to somebody on the street, but I can explain to you guys, just because it affects, you know, people's everyday life. I think in the interest of time, I'm going to show you this on my phone, but I was in the airport at SeaTac, Seattle. And this is something I was in my engineering, I showed in my engineering class. Try to make this as big as I can. This is kind of lame because I forgot about it until just now, but that's not bad. You can see that. You see what you're looking at there?
A big bridge.
So that's a bridge. And, you know, in this particular airport, there's like, I forgot, you know, like wing A and wing B. And so the problem is always in bigger airports, when they add on, it's like, how am I going to get, you know, all the people over there? Well, like in Chicago, you get on a little bus and you ride the bus across the tarmac, and then they let you off, and then off you go. Or there's like an underground train. Well, SeaTac decided, let's build like a sky bridge. But the problem is like, you know, airplanes have to go through there. So this is so big that we landed, and, you know, I've seen this before, but it's so big that we landed and actually drove underneath the bridge, you know, in an airplane. So they're big enough, like a 747 can drive underneath that sky bridge. And so, you know, but the point is like bridges are ubiquitous. So they are everywhere. And beams are, you know, we're going to do something simpler than that today, but a beam as simple as, I'd like to cross that stream. And so, you know, there's a tree and you cut it down and it falls, and then you walk across the bridge. But it's simply just a stick that is supported by something on both sides. And as you walk across it, if it's on the small side, it kind of bows down a little bit, right? And you can kind of feel that, and you're kind of wondering, whoa, what's going on? And interestingly, just a couple of days, I told you guys I did a wedding on Saturday for somebody, and it went really well, but I was like, oh man, I'm like 20 minutes early, and I'm like a time freak. So I pull off the road, and I think, I'm going to go over to where my grandparents are buried. I haven't been there forever. And and so I drive across there, and there's this kind of homemade bridge that goes across the creek, and there's a sign, and it says, cross at your own risk. This bridge is not inspected by the county. You know, I'm like in my car, and I'm thinking, man, basically they're just saying, if this breaks, you know, it's not our fault. And I get why they would say that. And, you know, of course I drive across it, and, you know, you can kind of feel it bow down. But my point is, like, this is everywhere, right? I mean, this kind of thing is everywhere. It's playful in your backyard. It's at the airport. It's everywhere. And so that's what I want to look at in this project. And I want you to understand it, because as I said, the neatest part about it is it's an amazing, if you will, sales pitch for the beauty of math. And the reason and it's amazing because, as I said, ultimately I'd like you to enjoy this, which means I'm going to sort of tell you too much, which is good. I'm glad I'm telling you too much. I want to help you get this problem right, because it's just too neat not to understand. And as I said, I can't explain this to very many people. You got to know, well, differential equations to get there. And so let me see if I can give you a proper introduction to this. Let's see what's on this sheet right here. So let's take a look at this. Moment, or torque, in engineering is a beam's desire to rotate, and force times lever arm distance is equal to torque. And you've probably seen that somewhere before. In other words, if I have you know, a kid on a teeter-totter or something like that, you know, and you put 100 pounds of force over here on the teeter totter, and this distance right here is 8 feet. Do you understand the 8 feet figures into how badly that beam wants to rotate? And so does the 100 pounds. You might be able to say, yeah, if you doubled the weight, put a 200 pounder on there, it's going to want to rotate twice as bad. And so it's both of those put together, and it turns out you just multiply them. So that'd be 800. We'll notice the units. This is important today. It's foot pounds if it's 8 feet. Now it could be 8 inches, but we'll say it's 8 feet and it's 100 pounds. You multiply those, you get 800 foot pounds of torque or moment. Engineers call it moment. Could you teeter totter there with a kid who was over here at, say, 200 pounds? We got some big kids here. 100-pound kid, 200-pound kid. Can you still, like, what's going to happen in that, case? Again, the untrained person would say, well, the 200-pounder is just going to pop to the ground. But torque is based on weight and distance. And you might understand fairly quickly, because this is a simple example. If you moved the teeter totter so that distance on that side was 4 feet, then that actually would be balancing. And so you could, teeter totter, no problem. Notice I got this, fun little picture over here of a whole teeter totter full of kids on both sides. And the interesting thing about a beam is, does it make sense? It's not just one load at one point. You have load everywhere. I'm going to erase this probably. Well, I guess I don't need to, but does it make sense? There's like also weight there and there and there and there. And like this thing is full of arrows because you have weight everywhere. So, think about that Sky Bridge I just showed you a second ago. Like, wouldn't that be full of people? Like, don't you have to calculate that to be jammed with people, like worst case scenario? If you don't, then you have to put a sign there that says limit 1 person at a time, maximum weight 300 pounds or something like that. But you're going to design it so that it can hold whatever its design weight is. But the idea is it's continuous load. It's not just load at one spot, right? And so that's the backbone of this. And so what this is all based on is, well, this equation right here. And so let me write that out a little more particularly, because notice I said moment is also equal to, so that's all I'm really going to do here is this is the equation. Now, what I still haven't decided is how much am I going to tell you about that equation? Well, at very least, you should be able to look at it and say, well, I don't even understand what that pertains to yet. But look, it's got a second derivative in it. And so do you agree that that's what we've been studying? And that's why I can stick this in right now. That's why this project lives right here in this curriculum for me and for you, is because that's a second order differential equation. And you should be like, hey, I know how to solve those. Cool. And so, let me give you at least a rough familiarity with, what are all those letters? What do they mean? And I did explain it on your sheet there a little bit, but I just want to give you a kind of a rough idea. And I have a picture at the top, but I want to draw like a simpler, uglier one first, just to give you a chance to make sense of these things one at a time. And so let's say, here's the big ravine, alligators are all down here. And so you say, all right, I'm going to put a beam across there and like walk across the alligators. And so there's your beam. And of course, do you understand that you don't even have to put any weight on it and that thing is not going to be straight? It's going to bend down under its own weight. And you may understand, based on that picture I just showed you, the weight of the bridge itself is the problem. If you put a person up in there and they walk, like the person's an ant. They don't even exist. They're nothing. Like a person weighs 200 pounds. That bridge weighs, 8 tons. And so, a person doesn't even matter. Like they might not even get calculated into it. And so you got to come up with some kind of a weight. And so we're going to put some weight on this bridge. And notice I didn't just say pounds. Why didn't I just say pounds? Because if I said the weight is 10 pounds, then the question is, where do you put it? Well, this is not just in one location, it's pounds per foot. So if I say it's 100 pounds per foot, then that means we got 100 pounds here and 100 pounds here and 100 pounds here and 100 pounds here. Like it's all the way across it. Most real applications have pounds per lineal foot. And by the way, for you future pounds per lineal foot, like that's That's how that unit is usually written, PLF in engineering. But that isn't as nice as pounds per foot. And so one of the things I want to get across to you today is how important units are to actually help you figure all this stuff out. And notice if I say it's 100 pounds per foot, even then it doesn't mean there's a 100 pounds here and then nothing, nothing, nothing. And then you get to the next foot and there's another 100 pounds. Does it make sense? 100 pounds per foot means 50 pounds every 6 inches. No, it means 25 pounds every 3 inches. No, it means like 8.3 pounds every inch. Like there's a million arrows there. There's not 4. You see what I'm saying? It's constant all the way across. And so pounds per lineal foot is how this is done, but it's understood that it spreads all the way across it. There's infinitely number of arrows. And so we're talking about infinitely many, infinitely small things, which is why this is a calculus problem. That's what we did in Calc 2. We added infinitely many, infinitely small things together. And so if I put that kind of weight on this beam, a certain amount of weight on it, of course, that's going to, make it bow down. It's going to bow down under its own weight. It's going to bow down under the weight of whatever you put on it. And so, okay, cool. Well, then the question becomes for us, and I'm going to draw this in more of an engineering kind of a fashion. So this is being supported by, concrete over there in the real world. And of course, the beam is not going to be like right on the tip top edge. It's going to, go past the structure a little bit and have a solid place to sit. But what we're really looking at is something that kind of does this. And I'm going to exaggerate the bend so that you can kind of see it. But that's what the bow is going to do. And so the kind of the bend or the deflection is the engineering way to say that. How much is that thing going to bend down? And so here's some of the key things that you need to understand. Then what we're going to do here is go out, say a distance Y, and if I draw this straight across, then this distance right here is going to be our distance X. And so do you understand? And by the way, I see some chat coming in, like speak up if you have something to say. I'm not going to jump over and look at that stuff kind of in a timely fashion. So if there's something in there that we need to talk about, interrupt and say it. But does it make sense at Y is 0? Where am I at Y is 0? I'm right here. Does it make sense X would also be 0? Like that's your initial condition here. So, again, you would see this in the book as this, Y of 0 equals 0. At X is 0, I'm sorry, a distance of Y is 0, X would be 0. And as a matter of fact, I'm maybe even kind of saying that backwards. Actually, I'm kind of looking at that now thinking, am I even mixing up those letters? Let me stare at my notes for a second. Yeah, I actually do have that backwards. Good. I was thinking that doesn't make any sense. This is the X. Let's just do this traditionally. A distance over X, then your bend down or your deflection or how far it drops below what it would want to be is Y. And so at X is 0, Y would be 0. And so that makes sense. But then if you move out at X is say, and again, the beam might be 20 feet long or something, but if you go out 4 feet, does it make sense? An engineer needs to know this. That's kind of the key. That's the backbone to this. You cannot build a $10 million sky bridge at SeaTac Airport and then discover, oh, when it was full of people, it bent down and hit the tail of the airplane that came through. It's like, oops, we shouldn't have done that. You can't wait till afterwards to discover you screwed it up and didn't build the bridge big enough. Does that make sense? And of course, in a smaller way, it's, this all engineering started with, I don't know if you know this, but started with the Iron Horse with railroads. That was the first time where you couldn't just kind of fall a tree across the river and like put a couple trees across the river and then get your wagon train across it. There wasn't any math going on there. It was kind of like, yeah, that tree's big enough, we'll be fine. But does it make sense that an Iron Horse, a train, is the first time it's like, we're gonna try to cross this river now with something that's actually really heavy, like technology advances and if you will, engineering started, at least in this country, with those trains breaking the bridge, falling into the river, and then nerds like us going, you know, how do we know how big to build that? It's like the first time you really got to take a serious look at that, design it. And so that's kind of where this math comes from. And so does it make sense that this is really important? What we are really after here is, what's the equation of that curve? Does that make sense? And as I mentioned quickly the other day, is what do you think that curve is? Is it a circle? Is it trig? Is it the sine wave? Is it like a chunk of a sine wave? We have all kinds of curves, right? Is it a parabola? Is it the bottom edge of a parabola? Is it the bottom edge of, you know, a circle? Is it a sine wave? You know, it's the bottom edge of a sine wave. It's the bottom edge of a parabola. Can you appreciate, like, I don't know. And by the way, there's also something called a catenary curve, which we're going to study in this class too, that I'll show you later on. But if you hang like at a power line, you look out your window, hey, look, a power line. You support a string or a rope from two different ends and it just kind of hangs down. That turns out not to be a circle, not to be a parabola, not to be a sine wave. It's a brand new curve. It's a curve that you don't know about yet, probably, called the
Cycloid?
catenary curve. Say again?
Oh, it's not a cycloid.
No, it's not cycloid either, which is also something you likely haven't heard of. There's just a ton of curves. And in the end, can you appreciate the problem here? Like, we need to come up with this, this whole thing hangs on this right here. I need to come up with the equation of that, because if I have the equation, then I own the relationship, right? I own the relationship for y as a function of x, and now I can predict things. Now I can say this bridge is full of 1,000 people, they weigh this much money. I understand, you know, how this is going to work, and I can predict how much it's going to bend, and then you can say that's good, that'll be okay. I'm gonna make that work. Now, what else determines how much that's going to bend than just the curve itself? Like, do all bridges bend down the same? You tell me, like, what else affects how much a bridge is going to bend down?
The material.
The material, like how flexible it is. This right here is the material. Basically, it's a constant that has to do with the material strength. Some materials are more flexible than others, like wood is more flexible than steel. Does that make sense? So that's the constant that represents. What else affects how flexible something is or how much it's going to bend?
Shape and size.
So one of the
Well,
things
shape really.
one of the things I can't do because I'm not at home, and some of you may know this, and I'm hearing things that I want to comment on, but if you were to kind of like, you know, walk across a bridge that you just dropped a board on the river, you would drop it that way because you can't balance on it if it's turned vertically. But if you took the same exact kind of beam and you turned it on edge, do you understand those two are not going to behave the same? Which one of those is more flexible, the right one or the left one?
The right one, probably.
The right one's a
you
lot more
stand, like,
flexible.
right on
It's
top
the
of
same
it.
exact board. Do you see what I'm saying? Like, it's the same exact board. It's made out of Douglas fir or whatever around here. But like one way, it's more deflecting. It has more deflection than the other. It's the same exact board. Let me just elaborate a little bit on that, just out of interest. Here's what happens to a beam if you bend it. So if I turn this sideways, you know, it kind of starts like that, but then if it bends, and I'll exaggerate this a whole bunch, it kind of does this. What happens to the fibers in that? Like, why does the wood not want to let that happen? Like, what keeps it from just breaking? And some of you studied some of this, and so you know things about it, but
Fibers up top are being compressed and the ones down beneath you are being kind of pulled apart.
yeah. Basically, the neutral axis is the middle of the beam. And if it's horizontal like the left one, the beam is kind of happy in an equilibrium. But But if you put a bunch of weight on this thing up here, whether it's just one force or a whole bunch of forces, then it's going to want to bend like that. But can you see that these fibers on the top are needing to crush together? I can illustrate that even with my fingers. If you bend it down like this, aren't the top fibers kind of crushing together? What's happening on the bottom fibers?
They're getting pulled apart.
Yeah, they're getting pulled apart or stretched, or whatever word you want to use for that. Engineers use what Ben was saying, because he's had a little bit of engineering with me as well as some of the rest of you. The top is in compression because it's being compressed and smashed together. The bottom is being stretched. That's tension. So tension and compression are the engineering words for that. But really the top fibers are getting crushed and the bottom fibers are stretching. If you have a weak material that can't resist crushing and stretching, then it's going to bend more. Well, that's effectively what this I is referencing. This is like the strength pertaining to the shape.
Is that why I-beams are shaped the way they are?
Exactly. Now think about I-beams for just a second. What happens to the neutral axis? Nothing. Those fibers aren't being crushed. They're not being stretched. Nothing happens to them, which means they don't matter. Does that make sense? Whereas the top and the bottom matter a lot. And can you appreciate the top fibers, the very highest fibers in the beam are doing the most of the work. And then the lowest fibers are doing most of the work. And the closer you are to the neutral axis, you're actually doing less and less of the work. The further you are away from the neutral axis, the more important you are to resisting that bending. Does that make sense? Can you just kind of feel what I'm saying without me doing the math to that? And so, yeah, it turns out that if you have an I-beam, there's kind of the cross-sectional view of it. Really quickly, does it make sense? What you're doing is you're taking your wood or your steel or your concrete and you're saying, let's put it all as far away from the neutral axis as possible, because that's where all the work's getting done. Don't waste your wood in the middle. These beams up here, do you agree that like all of this wood right here is no help in a sense? Yet notice there's a whole bunch of wood there going to waste. Now, in the case of like a tree, it doesn't really do much good to come in and just carve that out and throw it away. You can appreciate that's kind of hard to make. But if you're going to pour concrete to make a beam, which is how modern bridges are made and overpasses, there's like 50,000 of these in Medford. Next time you drive underneath that overpass of I-5 in Medford, just look up at that. And that's what you're going to see is an I-beam. I-beams are everywhere. Every house has got I-beams underneath it now, because if you make them out of concrete or steel, that's by far the most efficient way to do it. And so they have a higher I value. So that I is really just a number that has to do with the shape of the beam. Like, what are you really doing? And again, I can get into that. For now, I'll just tell you, like, this is how it's actually calculated. I said this on my sheet, but I won't go into that now because I just want to make sure we have time to get to the end of this. And so you can appreciate all of that. And then notice here then, notice there we have a second derivative. And then moment or torque, we said is a force times a distance, force times a length. I guess I'll keep it at what I did above, a force times a length. And so the simple way to understand this equation is that the change, what is dy dx? Notice it's not dy dt. This is not speed. It's dy dx. Well, dy dx is slope, right? Y and x is the equation, but dy dx is slope. What is d2y dx squared? What's the second derivative mean? Calculus 1 students?
Concavity.
It pertained to concavity. It told us concavity. And of course, you should find yourself going, man, I don't remember. I don't feel super comfortable with that. But most simply explained, slope is just change of something, right? So the second derivative is actually a change of slope. So one way to understand this equation right here that we're looking at, the foundational equation, again, the cool thing is you don't need to understand anything I've shown you so far to get this project right. I just want to give you kind of a conceptual understanding of it because it's no fun if you don't. But what this formula is actually saying, if you break it down, is the torque is proportional, since those are constants, that's just a number over there, to the change of slope. The change of slope is proportional to the torque. In a sense, that's the fundamental way to explain this equation. Now, if I tell you that these are just constants, those are numbers pertaining to the shape, you know, and down here, I said, down here, I told you how to calculate I, and you don't need to do that for our problem, but I told you how you can calculate it. So if you have a certain beam, then you just plug in B and D, which I think I showed on here someplace. B, where did I say that? Yeah, I guess I just said it right here. Width of the beam is B and the height of the beam is D. So in other words, if it's 2 inches wide and 12 inches tall, then you just plug 2 and 12 into that formula. And now you have a number. So if you choose a beam, boom, you got a constant for that. E, if you choose a beam, you know, oh, what's it made out of? Oh, steel. Well, then you look up the number for the flexibility number. Boom, you have a constant. You're really glad to see that, because if we're going to do this with respect to what we've learned in this class, we need equations with Y's and X's. Do you agree with that? I need Y's and X's. So when I see letters that aren't Y's and X's, I'm like, I'm going to jump off a building. This is no good. So the fact that E and I are just constants, like if I change this to be 5, second, you know, Y double prime equals something on the other side, it's like, oh, I'm glad that's a 5, right? But I'm not happy with this M. Do you agree with that? Because that's like the wrong letter. I need Y's and X's. If I'm going to take the derivative of this or take the integral like we've been solving lately, and we usually used Y's and T's, but that's what we did, right? Wasn't everything constants? And so we were kind of okay with that. I don't like M. M's a brand new letter. And so what I want to show you now is how to actually actually get the second order differential equation that I'm going to ask you to solve for this project. So let's look at this better picture up here. And let me help you understand it a little bit more. Let's see, do I have a better example of this? Yeah, let's do it here. So I gave you these. So let's just stare at a couple of things. And this is one of the things that I love about this project is how important these initial conditions are. So notice the beam itself. And so this little triangle in engineering language represents a support. This is called simply supported because the beam is just sitting on something, nothing else. It's not attached in some way. It's just sitting there. Quickly.
Does everything beyond the initial support not matter then?
Nice job. Everything beyond that support doesn't matter at all. Notice this is a fixed support beam. We'll get to that later on. I don't even think I'm gonna assign this to you. This might be an extra credit problem, just in the interest of time. But notice this one is fixed. What does it mean to be fixed? Well, if I had a wall here and a wall here, and I decided to put a beam between them, does it make sense I could actually run the beam back inside the wall a little bit if I wanted to? And now it's not just sitting there. Does it make sense to you that you could even take this wall away and that would still want to sit there if you had it attached to the wall in a fixed kind of a way? So notice when it kind of leaves the wall, if you will, when it kind of leaves the wall, it actually wants to stay level, and then it's going to start bending down after it leaves a little bit.
So what's the difference between like that would be a cantilever?
Yeah, what I just drew when I erased the other wall, that's a cantilevered beam.
And then the
So
one before
notice-
that was a simple beam. So why is that a fixed beam, I guess?
Fixed is if you have it attached to the wall as opposed to sitting on something. That's kind of the difference.
Oh, okay. It has, so the wall's the difference. Got it.
Yeah, the wall, how you have it attached to the wall. If you just drop a beam, and this is what this, and that's why simple supported is a good way to say it. Because if you just follow a tree over the top of a river, it's not attached to anything. You're just setting it there. And if you do that, isn't it going to do this? Of course, as I said before, it has to be too long. So isn't it going to kind of lift up off the ground over here? Does that make sense? Because you just sat it there. So it's going to lift up in the air. And then, yeah, this portion over here doesn't matter. Like that actually isn't helping. It's just there, if you will, but it isn't actually helping support. It's really just about, what happens from here to here. That's what simply supported looks like. Whereas if you say, no, I'm going to put the beam here. And of course, that's what it's going to do before you put any weight on it, right? It's just going to lay there and be, well, not flat, but it's going to be pretty close to flat. But what if you went in here and, like glued it to the ground so that it didn't want to do this? In other words, it doesn't want to lift up in the air now. Does it make sense? Now it's actually fixed. You've connected it in some way. If that was steel, couldn't you weld it across there? Couldn't you run it past and weld a foot of it? And then it isn't going to want to bow the same. And so in that case, after you put weight on it, it's going to have to leave the wall for a while before it starts to bend down. Does that make sense? Because it's glued down, it's welded down or whatever. And so that's kind of what I mean by fixed. Again, all I'm trying to do is just, I want you to understand the world you live in. It's just cool. It's cool to understand things. As I told you just last week, I want this to ruin your life. I want you to get to the bridge and everybody's like, let's go take a picnic. And you're the nerd that stops and like, no, I want to look at this bridge, man. This is so cool.
Or propose to our wives and wonder about the horizon.
Exactly. I want your wife to be like, what's wrong with you? I want to ruin your life.
I watched King Kong versus Godzilla, and yeah, after taking this class, that whole movie was ruined.
So notice, let's just do one thing at a time here. And so this thing is supported. We're after that curve there. We're after y as a function of x. The length of the beam is L. That's how long the beam is. Notice I'm doing that as a variable because is every beam the same length? What we're trying to do is find an equation for all beams, not just for one beam, but all beams. And so the length of it is L. And notice W, pounds per lineal foot, PLF. That's how many pounds per lineal feet you're going to put on it. So for instance, if I said W is equal to 100 pounds per lineal foot and L is equal to 14 feet. Does it make sense? You could figure out how much total weight was on that beam. If I take 100 pounds per lineal foot or foot and I multiply by 14 feet, then the feet will cancel and I get 1,400 pounds. Again, I see 16 messages in chat, so interrupt if there's something you want to say that needs to be said to everybody. So we have 1,400 pounds. And so if you say, okay, this beam has 1,400 pounds on it, and you're supporting it here and here, does it make sense quite obviously that each of those are going to have to push back at 700 pounds? So does it make sense if you had a 1,400 pound bridge like that and you set it in the dirt that it might sink into the dirt? Like you can't set a bridge on the dirt. Dirt might not be able to push back that much. So those supports are legit. Notice right up here, this is important. What did I say is pushing up right over there? Do you see why? There's a formula there that says WL divided by 2. Isn't that what we just did? Took the weight, pounds per foot 100 times the length 14. We got 1,400, and then I cut it in half. So that's what the bridge is experiencing. It's feeling itself being pushed on over there, right? So in the end, it's being pushed on over there and it's being pushed on right here. Do you see that's what's causing the bending? The sides are pushing up, the rest of the beam is pushing down. That's going to make it want to bow. That's what's causing the circular, well, it turns out not to be circular, but that's what's causing that dotted deflection curve. And so I drew it dotted because that's what's going to happen to it when you put weight on it. And so, all right, we're understanding lots of this stuff now. This distance right here is X. And the reason it's X is because that distance could be anywhere, right? Like we need an equation that will tell us how big Y is for any X we want to pick. And so if we said our beam is 14 feet long, you can understand an engineer might come back and say, okay, well, if I went 5 feet in from the edge of the bridge, then, what would Y equal? Does that make sense? That's what I need. I need some equation I can plug 5 into. And I actually get, something like 2 feet or something like that. I need to know how much it's going to bend down. That's what I need. I need a Y of X equation. You understand that? And so, this is the 0.52. Well, that's exactly what that's saying right there. I need that point right there, 5 times 2. So I'm after the equation for that curve. Now, secondly, there's one other thing you see here. What the heck is that? Why does that say WX with an arrow kind of being down on it? Why is that the case? Up here, it was like W times L for the entire beam. Why is it W times X right here?
Is it because that's where X is when it's, because this is getting kind of elongated, right?
Yeah.
So you're kind of in like a new spot.
Yeah, that's exactly right. In other words, right now I've chosen the spot X is 5. And so if you look at just this portion of the beam right here, does it make sense that doesn't have 1,400 pounds on it? That portion of the beam has, well, it's 5 feet long. It's still 100 pounds a foot. Like that portion of the beam would have 500 pounds on it. Does that make sense if I just ignored the other side of that? Again, you don't need to know anything that I've said so far. I'm just trying to help you understand the beauty and the magnitude of this. Don't let yourself, kind of be confused. I just want to play around with this. This doesn't, if all the purpose of this was for me to tell you the answer, then I would just tell you the answer and we'd be done. Let's go get some coffee.
We're trying to find the equation of that line, right?
Yeah.
How many points on it do we know?
We know 0. Well, we know 0, 0. That's it.
Oh, okay.
Well, we shouldn't know any points because don't we want to be able to plug in any point for any beam?
Exactly. We want any length beam with any weight possible. Yeah, we're still trying to do everything. And notice, does this initial condition also make sense to you? What does that mean?
Means that at the other end, it's also being supported at the same height.
Exactly. So if this beam is, as I said, 14 feet long, isn't that the point 14,0? And this point over here, O is 0, 0. Like that's the only thing I know about this. That's it. You understand that? Everything in between. At 5, do you agree Y might be -2, something like that? And I probably should, add a negative because isn't that going to go down? So the 0.5 -2 might be on it, but I don't know any of those points. All right. All right. Now we're ready. Oh, this was a bad decision. Let's do this a little more sophisticated style. So the right side of this beam, what I'm going to do here is go out a distance of X, and I'm just going to chop the beam off. And we're going to look at just that chunk on that one side over there. And so what forces are acting on that? It turns out the cool thing about this is, watch this. If I take, this is that little chunk of the beam right there. If I support this on this side and I just set my pencil and I'm about to let go with my right hand, what's going to happen if there's nothing on this side over here to support it? Like I just
Your
drew,
eraser's going down.
boom, the eraser's going down, right? The whole thing falls. Now, why doesn't a beam do that? Why doesn't my little chunk of beam that I just drew right here, why doesn't it do that? Why doesn't it just go and fall into the river?
It's held up by another piece of beam next to it.
It's held up by the other side of the beam. Does that make sense? Now, is it possible that it can't do that? Like it rips apart internally? This is one of the backbones to engineering. This is called a section view of the beam. And so it's because this chunk right here where it's connected to the rest of the beam is capable of resisting. It's effectively doing the job of my right finger over here. Does that make sense? It's the thing that's pushing back because it's connected to something. It's actually connected to something. But let me add the forces to this that we just described. Do you agree that, as I said earlier, that is WL over 2? That's the 700 pounds. So that chunk of the beam feels that happening to it, right? So there's that arrow pushing on it. But then right in the middle, that would be W times X. As I said, if that was 5 feet over, if X was 5 feet, and we said the beam had 100 pounds per foot in it, wouldn't this be 500 pounds? In our example, that was like 700 pounds. Does that make sense? And so notice those forces don't balance each other. What happens if you push down on something with 500 pounds and you push up on it with 700 pounds? What happens?
It rotates.
Yeah, let's rotate.
It's going to rotate and it's going to go up in the air. Does that make sense? Because net, isn't this being pushed up with 200 pounds? Like somebody's bench pressing and they're pushing it up in the air. That bridge is going to fly up in the air. You see what I'm saying? Now, it won't actually fly up in the air because of this connection over here. That's the thing that's kind of cool about this. Let's see, I got to decide how much of this I'm going to explain to you. I think maybe that's all I need to tell you. Okay, I can leave it at that. Take a look at my notes, make sure I don't screw this up. This stuff is hard enough. I actually did this on the plane on the way out here, but yeah. So now what we're going to do is I'm going to call this point, well, I called it earlier the point P. What I want to do now is because that's the only two forces that are on this with respect to rotation, I want to find the moment or the torque around point P. And as some of you are saying, like, isn't that going to want to rotate? If you look at just the right side of that, it's going to want to rotate, right? Just like when I support this pen over here, doesn't it want to rotate? It's not being equally supported on both sides, so it's going to want to rotate. Now, because of the structure of the beam, because of this connection over here, the beam can actually resist some of that, right? Because as it wants to bend down, is it going to be allowed to go down? No, because these fibers over here are saying no, right? They're like saying, oh, I'm crushing, but I can actually lift this weight. And so the beam is capable of providing a force right here. Now, what you need is for the beam not to rotate. An engineer's job is like, hey, look at that beam over there. What do you want to see? I want to see it not moving. If that beam is going down, you're fired. If that beam is rotating, you're fired. Like, I need that to not move. Like, that's the first engineering class I teach. It's called statics. I need it to be static. I need it not to move. So let's add up. You know the language of calculus. Let's add up all of the moments. And see what we get. Now remember, moment, torque, is force times distance. Force times the distance. So right here, we have a force of 700 pounds, which we're calling, WL over 2. It's because, we're going to do this in every case. How far away is that from point P, the point around which we're choosing to rotate?
0. Oh, wait. Never mind. It's halfway away from the point.
I'm looking at point P right here.
Oh,
How
point.
far is this force away from that point?
X far.
It's X far away. You agree with that? Now, again, we can't say 5 feet because then we'd only be calculating one beam and one problem. We want to do all beams. So it's a distance of X. That force times that distance. Now, again, in our example, that would be 700 pounds times 5 feet. That'd be 3,500 pounds of desire to rotate. So that force wants it to rotate with 3,500 foot-pounds of force or torque or desire. It's like it wants to rotate really bad. Is it going to be allowed to do that? Well, if that was the only force on it, again, you're fired because the beam rotated and all the people fell and they died. What about this one? What about this one, that 500, that WX? How far is it away from P?
That's the W over X, right?
That's the force. So we have this force times this distance. And now we have this force times, well, what distance? How far is the 500 pounds? How far is
Half
that away from
pi.
B?
Half a
Say it
pi.
again?
Or I mean, X.
P
Exactly.
minus.
Half of X. Do you agree with that? It's in the middle. Now, again, realistically, the 500 pounds is spread all the way across that. But one of the cool things about engineering is you can treat it like it's just one force in the middle. But the key is it would be in the middle. So does it make sense to you that that would be a distance of X over 2? Now, what about signs? You know this. Are those both positive signs? Do I add these together? Do I subtract them? Is this one positive and this one negative? Or are they both positive? Are they both negative? Are they both working together? Or are they working against each other?
One should be positive and one should be negative, shouldn't it?
Why? You're correct.
Well, one is pushing downward on the bridge to be negative, and then you have a force pushing back up, which should be positive.
Yeah, again, around the point P, doesn't this one want it to rotate that way? Whereas this one wants it to rotate this way. And that's kind of good because that means they're working against each other because we don't want it to rotate. So we need something to push back, right? If the first one is 700 times 5, 3,500 foot-pounds of desire to rotate, we need the other one to push back. Well, notice the other one doesn't push back enough. In our example, 500 pounds times a distance, again, we were calling distance X 5 feet. We were sort of treating like this, like it was a 5. That'd be 500 times 2.5. That's not very much. So, and you know the convention, which one of those is positive and which one is negative?
The WX should be negative.
This direction, what direction do we call that?
Counterclockwise. I don't know.
Yeah, that's counterclockwise. In
Oh,
the
okay.
language of trig, that's exactly right. In the language of trig, if you're going to rotate something, what direction do we call that? And what direction do we call that?
Positive and negative theta.
This
I mean,
is this
I
one
could-
is positive and that one is negative. Isn't that what we call that? If you say rotate negative 30 degrees, doesn't that mean go this way 30 degrees?
Is that the right hand rule?
It's a little simpler than the right hand rule, but it's going down that road. So actually this one is the positive one and this one is the negative one. Does that make sense? And then
Yeah.
lastly, and again, I want to caution you, you still don't need to know anything I've shown you yet to get this project correct. So, if you're feeling lost, you should. I'm trying to teach you all of engineering and statics in like an hour. you should be lost. That's okay. But then lastly,
Is that because of because torque comes from angular momentum that we're doing it with the signs with theta?
yeah.
Instead of- okay.
So the fact, all the positive and negative here really mean is just they're working against each other.
Right.
If this was going this way, then they'd be, working together, and that'd be very different. And then notice this M that I drew right here is also agreeing with WX. In other words, that M is also positive.
Now, real quick, we chose WX to be halfway because that's where the center of gravity is on this little piece.
That's exactly right.
Okay.
In other
Just-
words, although technically there's a million arrows here going across this, totaling 500 pounds, but each one by itself might be 2 pounds. We can treat it as though it's just one huge 500 pounds, and then we'd have to put it in the center of mass or in the middle of that thing. Does that make sense? At least a little bit.
What is the plus M that you put on the end of our equation?
That is the fact that the connection that this beam has to the other part of the beam, which is why I drew it cracked here, it's connected to the rest of the beam. And so the rest of the beam, if our little section wants to rotate like this, the connection it has to the other side of the beam is going to push back up and say, no. You agree with that? Like, this connection is not going to let this fall. This is going to push up and say, no, you can't do that. So there's three forces acting on that section of the left-hand section of the beam. Do you agree with that? At least roughly.
The net torque would be 0.
Nice job. And this is really important, don't we need this all to be equal to nothing? Why do we need it to be nothing? Because your bridge better not rotate. If it rotates, you're fired, right? Everybody dies, you're fired. All right, we're ready. All we got to do now is solve for M. What is M equal to according to that formula? All you got to do is look at this part right here and solve for M.
WX squared over 2. Or I guess it would be
Yeah, that's right.
minus WX squared over 2.
No, because actually you're right. Because if I leave M on this side, then that would actually be minus, right? Because I got to subtract it to the other side.
Right. And then
I never like putting minuses in front next to equal signs because they end up like getting lost with the equal sign. Have you done that wrong before on your work or on a test?
Oh yeah.
No,
I
never.
obviously meant to say it the other way, so I can.
And then
the other one added.
the other one would be added, right? So the other one would be WL over 2 times X. Now, why did I write it that way? Remember, WL and 2 are just constants, and the X is the only real variable here. In other words, this is like 5X minus 6X squared. You see what I'm saying? Now, good news, friends, we're there. What was the guiding equation behind all of this? Here's a hint. It's that one. Remember how I said we're okay with, we see here that Y is the dependent variable. Think very carefully about this. Y is the dependent variable, X is the independent variable. Why is that in this picture? Because you're welcome to choose X to be any location you want independently. Again, we said, hey, what about 5 feet? But as a result of that, you're just stuck with the deflection or the bending there, right? You choose 5 independently, Y depends on that. If you choose X to be 0, hey, good news. We know the answer to that one, Y will be 0. By the way, we'll get to this later, but where would the biggest Y value be? Where am I going to find
Half
the largest
X.
Y value?
X over 2.
Halfway across. Now that'd be half of L, not half of X. X would be L over 2. Does that make sense? But it'd be in the middle, right? Isn't that where the biggest is going to be? We'll get to that later, but. And so Y is our dependent variable, X is our independent variable. I need Y's and X's in my equation. I'm okay with these because they're constants. And what did we just figure out that was equal to? Didn't we just figure out what that was with constants and X's? This is very good news. It's very exciting. I'm getting chills right now, even though I've spent hours and hours trying to figure this out and understand it. I did this on the plane actually when I was flying out here, and I didn't tell the person next to me because I knew what reaction I would get. Here we go. E times I equals, no, not equals. equals the second derivative. Let's see, how am I going to write that? I'm going to write it the way it was written up above. The second derivative of y with respect to x. That now equals what we just said, WL over 2. And that's why I wrote it that way. I didn't write WLX over 2. I wrote it as WL over 2 because that just represents a constant. And then it'll be multiplied by x. And then W over 2, which is also a constant, multiplied by x squared. And so it's extremely important to understand here that we will be treating all the other letters as constants. E is a constant, it's just some number. I is some number. W is some number. L is some number.
Don't forget 2.
And 2.
So we could just solve this with separation of variables.
Yeah, so now here we go. So this is a second order differential equation. Now here's the really good news about this. Notice there's no y prime term, like what you were used to seeing before. I'm going to erase this, but you were used to seeing things like 5y double prime plus 6y prime minus 7 equals 0, stuff like that, right? So it had a y double prime. And of course, that's that right there, right? But it also had a y prime. Well, notice we don't have a y prime. Again, real differential equations is not somebody giving you some irrelevant equation like that and saying, can you solve this? We just wrote our own differential equation. That is the only access you have to this bending problem, is it comes with a second derivative in it. More simply, like we had to get pretty sophisticated to answer this green question here. But remember, if your equation has a derivative in it, let me just show you a super quick example. If I told you dy dx equals 5x plus 2, what's the easiest way to solve that for y? You're talking, Thomas, unmute. I see your mouth moving. If you're talking to us, maybe you're not talking to us.
Is it taking the integral?
Exactly. Like this isn't that hard. This is just take the integral. Now in our problem, we're going to have to take that twice. But if you came back to this problem and said, I'm going to take the integral of both sides, the integral of the derivative of y is y, right? Like that's sweet. I just got rid of it. What's the integral of 5x plus 2? Notice that's just got x's in it. Thank God. I'm so glad it isn't 5y plus 2, right? Because our independent variable is x. The integral of 5x, of course, is 5x squared over 2. The integral of 2 is 2x. Isn't that my equation? Well, no, it's not. Why is that not my equation? It's really important. What's missing?
Constant.
Plus some constant. That constant is going to be essential for this problem. If you don't have that, you lose. Like it doesn't work. Like that's all you have to do here. Do you see that this is the same exact problem? Except for the other side is squared. Again, you got to see this is nothing more than like 5x minus 7x squared. Like I can take the integral of both sides of that.
I don't know if it was specified in the problem, but is our initial velocity going to be 0?
No velocity, but we don't know. Our initial slope, we don't know. In other words, y prime, take a look at this. Y prime of 0 equals, we have no idea. We don't know that initial condition. Why did you ask that, David? You asked it because isn't that what we were given in our textbook problems? Like we had a y of 0 and a y prime of 0, and we have a second derivative here, so aren't going to need that. But does it make sense we don't know? Because what is y prime? Y prime's that slope right there, isn't it? I don't know what that slope is. If it was a lot of weight, isn't it going to be a really big slope? If it was not much weight, it'll be a lower slope. It's like, I don't know. We don't know. It's not good. We don't know. But we do know these. So just so that it's all down in one place, I'm going to write those down. We know y of 0 and y of L are 0. Now, you don't need to know anything that I said. I could have started today and just said, hey, can you solve this differential equation? And we'd be in exactly the same place. I spent an hour giving you at least a shot at some conceptual understanding of where this amazing, ubiquitous second order differential equation comes from. Now I'm just saying, can you solve it? Can you find the equation y is a function of x given these initial conditions, ignoring, frankly, E, I, W, and L?
We would need to get a particular solution, we'd need that initial y prime value, wouldn't we?
Nope. You'd think so, but you don't.
Yeah, because there's no actual normal y prime showing up in the differential equation. We don't actually need it.
By the way, notice for the fixed support, here you do know it. Y prime of 0 is 0. If it's attached to the wall, isn't its initial slope actually 0? We would know it in that case. You have a totally different set of initial conditions. It turns out that the fixed support beam, the cantilevered beam, and the simply supported beam all start with this exact same equation. The only thing that changes, and you can appreciate those are three totally different cases of how engineering works in the real world. They all three start with this exact problem. The only thing that changes is what initial conditions do you have? And they make totally different equations, which is amazing that it's one differential equation that is all three cases. Unbelievably cool. So your problem is simply supported beam. Make the calculation. If you want to tackle the fixed support and the cantilevered beam for extra credit, or you're just interested, or whatever the case may be, like that can be kind of an ongoing conversation that you and I have for extra credit. And again, this is the kind of extra credit that would be worth a lot at the end of this class, both because you're showing interest as a human being and because it's like a challenge. And so, you're not going to just finish this on your own. Like, this is hard. There's a lot to know here. Because those other cases, actually, I just lied. Those other two cases, let me think for just 1 second. Actually, this is the case for the fixed and the simple, but not for the cantilevered one. This part over here is different for the cantilevered one. So if you do take on the extra credit, save the cantilever one for last. Try the fixed support one. That's the exact same setup, but it's not true for the cantilevered one. So I'm going to shut up for a while and give you time to try to solve that. This is actually not that hard to solve. As long as you understand that, hey, I'm going to have to integrate twice. But I'll give you time to think about this, and I'll ultimately ask you a more specific question. Again, you're more than welcome to connect outside of class on Discord, and I would prefer to have one paper from 3 of you with all your names on it eventually. But don't let other people do this for you. I won't know. But this is too cool not to understand. That's why I'm hearing my grandkids. There's a microphone in their room. And as I said before, some of you will be able to get this on your own in a relatively short period of time without any help. Unbelievable. Good for you. That is totally cool. Some of you are going to need all kinds of help. I don't care. I want you all to get it. If I need to give you 10 hints, I want you to get this with hints that I give you under your own power. So don't do what you can not to let someone else do your thinking for you here. I see now
So-
that you guys are talking about units in the chat. Maybe at the end of class, I'll go over how the units on this work. The fact that these two sides have the exact same units is really cool to look at. And yes, I did this in our system, but it's only because I wanted you, I knew you spoke our system better than metric. So I thought you'd conceptually pick that up faster than doing this in metric, but they both work.
Also, from a practical perspective, it feels a little bit weird to have a beam specified in like newtons per length.
Correct.
So you'd have to do an extra unit conversion or have the problem feel kind of weird.
Yeah.
So
You're one sharp dude, by the way, Landon. I'm
Yeah,
always
so one-
afraid when you ask questions. I'm like, oh, I'm not going to be able to answer that.
So one thing I was my initial instinct when I was looking at the I guess slice off diagram there is to not actually take the sum of the moments around point P, but to actually just take the sum of the moments around the origin. And
Yeah.
it works out, but it's not quite as fun.
And Landon is asking that because he did take statics from me. And so he's got a lot more background in how to do this. The cool thing about taking it around P is, remember, Landon, P is anywhere, whereas the origin is kind of stuck in a location. And you're right, that point P could be anywhere, and it could be at the origin. But saying
Yeah.
it doesn't have to be at the origin like I did makes it a little more open-ended. And off the top of my head, to your point, I actually am not sure. You're saying it gives you the same equation, but it's a little bit harder. Actually, I don't know.
Yeah,
saying
so
that.
let me actually verify it. Then I've done my math correctly here real quick.
Yeah, let's see. And that's so here's what I want to do, because I don't want the first person that figures this out to say, is this the right answer? And then, and then I say yes, and everybody kind of knows. So I'll set up a chat room. Let's see. I can't remember how to do this. I haven't done this in a while. We'll go in a chat room. So let me figure this out. Breakout rooms. Assign manually. Let participants choose rooms. Let's see. I think I'm creating a breakout room right now. So I think I have a breakout room set up. So there's a breakout room, and can you join? Can you remind me? What do you guys see? Can you go in that room now if you want to?
Yeah, we
You
can
have a
go.
card?
Yes.
Sweet. So you just tell me out loud, hey, can I check my answer? And then you go in the breakout room and I'll go there with you.
Can I check my answer?
Yeah. Still hearing kids screaming. Why am I hearing kids screaming? What do you got, David?
Do the constants just cancel? And then I think I got, here, I could just quickly write it on the screen. It'd probably be easier.
Yeah, I agree.
I left it implicit. Could be wrong.
Ultimately, that needs to be y, not y squared.
Okay. So my constants ended up canceling out. Could be wrong. This is what I got.
How did you end up with y squared? Because it's a second derivative of y, so it should just be y. Y squared should not have showed up there. How did you manage that?
Second derivative of y? Well, I integrated twice, so maybe I did that wrong. Because I got
I think you integrated twice and you thought that's going to leave a y squared behind, but it just leaves a y behind.
okay. Well, so when I had EI and then I had D2y, and then I
Right.
integrated that.
Yeah.
And that gave me a y, right, times the E and the I, which are A now. And then that left a dy behind, I thought.
Correct.
And then when you integrate again,
Oh, I see. I gotcha. No, it doesn't leave a y. If you integrate if you integrate y double prime, you get y prime. There's no y. You just have y prime.
oh, okay. That makes so much sense. Okay,
Yeah.
cool.
Wonderful question. That's just a wonderful question.
Okay, and then so if there wasn't a root, then would that be correct?
You're barking up the right tree, but no.
Okay, I'll do it again now that I've kind of thought about it. Now that I have a different. Cool. Do you have any idea, any advice where I'm going wrong, or would you need to see my work?
Well, tell me what you did when you took what you got when you took the first integral. Not you gave me both, but tell me what you got when you got the first integral. You can just say it out loud because I'm looking at my answer.
You know what? When I integrate, I think I multiplied that 2 over because I got a y squared over 2, and so
yeah,
it would turn back into 12 and 24. Well, so okay, so when I integrated the first time, I got WL over 4x squared minus W over 6x cubed.
You nailed it. That's totally true, but you've kind of screwed up the constants. They don't cancel out. Look at that equation. So here's where you are. If you look at that equation right there and you plug in 0 for x, you will get 0. Do you agree with that?
Yes.
0 for y. But if you plug in L for x, do you get 0? No, you don't.
Right.
And you need to. If you put in L for x, you don't get 0. So that means this doesn't work.
Okay.
So
well,
go back and think about your constants more.
That yes. Okay. Sounds good. Cool.
Nice job.
Thanks.
Just had a super productive discussion with David, who's quicker. Like David's smarter than I am, faster, like mentally. Super productive one-on-one discussion. I'd love to have one of those with every one of you, like wherever you're stuck. So if I didn't, like if I let him just say that out loud to the whole group, that would have screwed it up for you. So I'd love to. Who else is ready? Let's go talk.
Ready right now.
Okay, I'm heading over there. I'm heading there, Ben.
Cool. I'm doing it right now.
Me too. Fire away.
All right. So where is it? Right here. Okay. So I got for my final answer, y equals negative W over 2EI. Open parentheses 1 over 12 x to the 4th minus L over 6 x to the 3rd minus L to the 4th over 12 close parentheses.
Sweet. I wrote mine differently, so I wasn't able to do that on the fly.
Yeah,
Pull up a whiteboard and write it.
Yeah, that would probably be a lot easier. Okay. Yeah, so I took the something out of all the parentheses.
Yeah. I did that too, but I took a different thing out, so I just wasn't able to keep up. Write it the way you wrote it. You don't need to rewrite it any other way.
Cool. It's my final form. There we go.
Minus L over 6 WL cubed. WLX cubed over 12 minus L. Okay, so the question I have for you is, does that satisfy the initial conditions? If you put in X is 0,
oh, good point.
you get 0. if you put in X
Yeah.
is L, do you get 0? The answer is no, you don't.
Oh, you're right. Yeah, if I plug in, yeah, that's a good point. Yeah, so how do I?
So I'm going to let you think
I
about
got my
that.
CQ 0. Okay.
Keep thinking about that. You're doing
I'll look
awesome.
at-
You're doing awesome. I'm going to go back. Let's go back.
Okay.
Yeah. Which I did y, and then I integrated it again, and I got y squared over 2, and then that screwed me up, kind of.
You integrated a third time?
No. I just integrated wrong.
Oh, Doug, I need you, man. I need to go in the breakout room.
Okay, let me say one thing to everybody before we go.
Okay.
Both David and Ben are smarter than me. And again, I say that as a tremendous compliment. Obviously, I understand this better than them, but it took me way more to understand this than it will take them, right? That's a IQ. Like they probably have a higher IQ than I do. Many of you do actually. Took me a long time to figure this out. I said the same thing to both of them, which is, and so I'm saying this to all of you right now. I said, is y of 0 equal to 0? And you're in the equation you just think you told me. Is y of L equal to 0? The answer in both their cases, no. Your equation does not meet those initial conditions. The integral taking here is actually pretty easy. The initial conditions are killer. Like you really got to think about them. So check that. All right, Connor, you ready?
Yeah, let's do it.
Do it. So if you want to write something, pull up a whiteboard because a lot of times you're writing it different than me, and then I.
Yeah. So let's get prepared to talk to somebody who's not smarter than you. We're near the same level for sure.
By the way, I'd say you and I are really similarly cut out of the same kind of cloth. By the way, I've been very impressed at how interested you are, excited you are in math, and you make mistakes in the same fashion that I made and make them. So
I make mistakes in every fashion. Failure's my thing. I like to get past it. So basically, I did, d squared y over dxy equals WL, obviously everything we wrote. So WL over 2x minus WL squared over, oh, sorry, that's not supposed to be now. W2 squared. And then I minus the EY, right? So.
No, that's a huge dumb algebra mistake.
Is it?
How do you get rid of EI?
I subtracted it from the other side.
But it wasn't added to the other side. So how do you get rid of it by
multiplied,
subtracting? Mm-hmm.
Oh, so you divide by.
Mm-hmm. And that's just a constant. That's just a constant. So you could just put it out front and just ignore it for later. Kind of say like, oh yeah, there's a 1 over EI out in front of that whole thing. Does that make sense?
You put it like out here, or do you put it like right here?
Second one. Yeah, if you want rid of it on that side, put it on the other side, but just kind of think of it as out front and ignore it for later. In other words, it's 1 over EI times parentheses WLX over W over 2x squared.
Does that affect the derivative or the integral?
No, that's exactly right. Because like, isn't the integral of 4x squared? Couldn't you just like pretend the 4 isn't there?
Yeah. Okay.
The integral of x squared is x cubed over 3, and then like bring your 4 back in afterwards.
Perfect.
So
okay. So then you double integrate. And I guess because that happens, I made a dumb algebra mistake, but it's an easy fix.
Yeah.
WL over 12x to the cubed minus x to the 4th, and then
nice job.
We have over EI.
Yeah,
all over EI. And so basically,
but what important thing is missing from those integrals?
the C. Okay.
And you did it twice. You did an integral twice.
Yeah,
so
I did. But do those constants can't combine to another constant?
No. Why not? What happens when you take the first integral? What happens? You have a plus C, right?
Yeah.
But what happens when you take the integral of that c the second time?
It grows an x.
Bing.
Grows an x plus
Plus-
c.
There we go. And
Wow.
by the way, those are also divided by EI,
They are.
right?
Oh, because do we divide EI at the very end? I see. I divided it at first.
That's exactly right. Now, what you have to do is come up with those two constants, and they're different. You know, it's like C1 and C2. They're different, and you got to come up with them in such a way that when you put in 0, you get 0 for Y. And when you put in L for X, you also get 0.
Okay. Wow. So for a second, so what does L stand for in this when it says YL equals 0?
L is the length of the beam. In other words, when you get to the other side of the beam, the deflection is also 0.
I thought L equaled X.
X is anything between 0 and L. So if your beam is like 14 feet long, X could be 7, X could be 6, but X can't be 16 because the beam's only 14 feet long.
Okay.
So
Did we
L is the
establish,
length of the beam.
did we
and so-
establish it was 14 feet in the front part?
Not for real. I just did that as an
Okay.
example because it's harder to do this with letters than it is with numbers. Because we need L not to be 14. Otherwise, then we've only solved this for 14-foot beams. We need to solve this for all beams in the universe.
Gotcha. Okay.
So L is a constant, but it's the length of the beam. And so however long the beam is, when you get to the other side, Y is back to 0 again. Does that make sense?
Yeah. So then all you're doing is setting this equal to 0 and then solving for the two constants or the two C's, right?
Yeah, but the problem is it has to work for X being 0 on the left side of the beam and X being L on the right side of the beam. And that's how you're going to find the two constants.
So this is set up kind of just how we did with the homogeneous equations, right? With the multiple order homogeneous equations.
Mm-hmm.
All right.
You're
I think
there.
that's a good jumping off point for me. Yeah, thank you.
Okay, back I go.
Sounds great.
Who else is ready?
Can I check my answer, Doug? Oh yeah, you can come too, Thomas.
Yeah, I'm sticking with folks that haven't been over there yet. Thomas, I saw you. Let's go over there. So pull up a whiteboard and scratch around.
Let's see. I don't know how to do that.
Good. That's a good takeaway from this. So actually I'm thinking the same thing. What options do you have? Chat participants. No, it's not participants. Reactions, breakout rooms, share screen, video, mute. Stop recording. View. Huh.
I could Google it real quick.
There's only so many places you can click here, so how hard could it be?
Let's see. Yeah, I kind of wish I had a notepad for this very reason.
Everybody that's been over there so far has just been doing it with the mouse, but it's like we can understand, even though it's all first grade looking, who cares? View, review, speaker view. That's weird. How come we can't?
Let's do- Screen share, click whiteboard.
There we go. That's it. You got it.
So we have EI equals, and then WL L over 2x minus, what was that? WX to the third, no, WX squared. So my first instinct is to, oh, I'm skipping ahead. That's a dy2 over dx
You're fine.
And that's
Totally
what that
get it.
says.
Yep.
So my first instinct is to get this right here by itself. So then
Okay.
divide the EI over.
Okay,
So
fine.
we have the dy dx. We'll just put an x. And then is
Yeah,
that so WL over the EI to X, and then WX squared over EI.
by the way, that WX squared was also over 2.
Oh,
Earlier, so just throw a 2 down there. Yep, you're good. That's it.
and then so then we take the derivative or the
Yes.
integral,
Yes,
but the
yes.
double integral. And then when we do that, this grows a 2, right?
Yeah. Uh-huh.
And then so do we keep all of our constants, or are these starting to?
No, you just keep all the constants. They just come along for the ride.
So then this is where I'm just kind of like, there's so many letters going on here. It's getting kind of like, whoa.
Yeah. But that's exactly why I thought of it. That's why I wrote the WL over 2EI just out to the front, because it's ugly, but it's just a constant.
Okay.
It's like you're taking the integral of 5x right now. That's it.
Okay.
Nice.
So then
Great
we just
job.
have to remember we get a constant at the end.
Correct.
And then when we integrate for a second time, we get an X
Yes,
and then plus C.
that's exactly right. And those 2 C's are different, right? So one C1 and one C2.
Well, then this is kind of where I hit a roadblock. So now we solve for this equation.
So see, what you need now is you need to figure out what C1 and C2 is. And they're going to be constants, but
Okay.
unfortunately, they're not going to be just like 5 and 7. They're going to be W's and L's and things of that nature. But the
Mhm.
key thing is when you plug in X is 0, the Y on the other side better be 0. And when you plug in X is L, the Y on the other side also needs to be 0. So how can you find a C1 and C2 that bring that about? Not easy. Like you're-
Okay.
But you've got it. Like that's the problem now. You've totally got it. So work on getting those, and you're right. Like the integral of X is X squared over 2, and the rest of the constants come along for the ride. That's not that hard. The hard part is, how do I find C1 and C2?
So that's our $1 million question that we're looking for.
Yep.
Okay. Cool.
Nice
Alright,
job.
cool.
Let's go back.
Thank you.
Nice work.
I think
Now, let me say something to everybody here. Your biggest X on the other side of the dy2 dx squared thing, the biggest X over there is X squared, right? What's the integral of X squared? It's X cubed. True? What's the integral of X cubed? X to the 4th. You agree with that? That's the answer, by the way, to the curve earlier. What kind of curve is that? It's an X to the 4th. Like none of you would have guessed that. It's an X to the 4th equation, but don't X to the 4ths have curves in them? Let me show you something kind of cool. By the way, Thomas, I just left the room like you were saying something right as I clicked exit. So if you need to say something.
I was just going to say the guy on the airplane next to you probably would have asked to enroll in the class.
He's like, stewardess, can I change seats? I mean, is this fascinating? I mean, you got to be the kind of person, but so I want to show you something really quick. Now think about this. Do you guys know what X to the 4th equations look like, don't you? What does an X to the 4th equation look like from Math 111?
It's like a parabola, but with a flat thing at the tip.
Yeah, 4th degree equations look like this. They either look like this or they look like this, right? it turns out that, and by the way, is that fourth degree equation, is it a negative or a positive? Which one is it? Which one of these two? Is it a W or is it an M?
It should be the negative.
It's the negative. Do you know which one of these is the negative? From Math 111, it's been a while. Do you know which one it is?
The one pointing, the one on the right.
Is it the M or the W? You might be wrong. Like, take an educated guess. Like, isn't this what y equals x squared looks like? And isn't this what y equals negative x squared looks like? Which one is negative x to the fourth? Just like the parabola. It's this one. So where's our beam in that picture right there?
In the center.
In the center. It turns out that's what a beam does right there. It's a fourth degree polynomial. Again, the cool part of this is like you studied just, wasn't this topic that I just raised really boring to you to some extent when you learned Math 111? Maybe not. You guys like math, so maybe it was cool to you. But you can see why most people are like, whoever needs to know this stuff. I hate this stuff. The answer is, well, have you ever walked across a bridge? Then you do. Well, you paid somebody to. But isn't that cool that it's like a negative fourth degree polynomial is turns out what the equation is? Unbelievable. All right. Who else?
I'm kind of stuck.
Okay, Raymond, let's head over there.
Okay.
So if you can ask me your question verbally, do it, but more likely.
Yeah, is there a whiteboard?
Open a
How do I
whiteboard,
draw on that?
scratch on there and make it ugly.
How do I draw on the whiteboard?
Go to share screen, I think.
Gotcha.
That's it.
Okay, so this is what I have for my y prime equation. I don't know if it's right or not.
Yep, integral of x is x squared over 2. Okay, hang on one second there.
Yeah. Just gonna add that. That's what I got.
So there was no L. One of those equations had no L in it.
Oh, my bad.
Wondering, like
I
which
have to
one?
have
It's the
that
cube one. Yeah, that's just W, isn't it?
2.
Oh, there we go. Yeah, got it. Okay.
Yeah, so this is, and I understand I need to take a second integral here.
Yeah. Now, before you do that, clean up that mess. Like
Yeah,
call that WL over 4 EI. Like that's your coefficient. You see what I mean by that? And EI is on the bottom too. It's not times EI. It's down there with the 4. So that's ugly, but it's just a constant.
gotcha.
And that's multiplied by x squared. You see what I'm saying?
Mm-hmm.
So now it's just junk times x squared. Same thing with the other one. What do you got? No, connect the 6, connect the 2 and the 3.
Maybe right there.
Yeah, now get rid of the 2 because it's just W over 6. It's
I
going to
see.
make less mistakes if you clean up that mess.
And the EI would go here or with the
Now,
6.
you don't want 2 fractions. Think of it as cleaning up fractions is really just multiplying by the reciprocal. In other words, if you look at the top, you say, hey, what's W over 2 divided by EI? Isn't that W over 2 times 1 over EI? You multiply by the reciprocal because EI is kind of like a whole number. It's like 5. Well, what's dividing by 5 is multiplying by 1/5.
I see. Okay.
That's it. That's it. So try to ignore those constants and just pretend they're like 7 or whatever. Good. Now
Gotcha.
take the integral of that. What do you get?
Of just this right here.
Yeah, because that now is actually equal to y prime.
I'm gonna have more of these again. Okay.
But
I'll
notice, yeah, so clean that up, but don't do it now. You're doing great. Keep going. Yes. Yes. And do you understand that those two C's are not the same C? So you might want to call them
Yes.
C1 and C2 or something. You totally have it. And that's equal to y. Like you've now taken the integral of the derivative twice, and now it's just y. You have y equals. You got it. All you
Okay,
need
cool.
now is to figure out C1 and C2 in such a fashion that if you were to plug in x is 0, y is 0. If you were to plug in x is L, y is 0 again.
Okay. Yeah, because when I got this this thing up here, I saw that and I was like, that can't be right. And that's how I got stuck because I was trying to clean it up. Okay.
Now, the thing is, the only hard part of this is C1 and C2 are not just going to be like 7 and 6. They're going to be composed of your other constants, like there'll be W's and L's and E's or, something of that nature.
Oh, okay. They're not going to be numbers. They're going to be
Yeah. And then
more.
the other
complex.
thing that's a little confusing about this is, had you left E and I on the other side, like as constants,
Mhm.
and just kind of ignored them for a while, does it make sense? The right side would have looked the same, except then you could have divided by EI later.
Oh,
Well, for that reason, everything on that side is divided by EI, not just the first two terms. The CX and the C2 are also divided by EI. You may be better off just putting 1 over EI out in front of the whole thing,
okay.
because those are actually divided by EI as well.
So like I'd have it out here and I'd take all of these out.
Yeah, just get rid of all the EIs. And that way they'd be with everything, if you will.
Okay, that makes sense. Cool.
You totally got it.
Okay, thank you.
Let's head back.
All right.
Your boundary condition. Go a distance of L this way.
Okay, distance.
And
of-
so you're going to have a curve down here. And you're going to want to evaluate your initial conditions here and here. Right.
Yeah,
And so the value at this curve is y of L. Right. And we're saying that it's also at our y equals 0. Right. So we evaluate our function y at the point x equals L.
Okay, I think I get it. So you're not plugging in 0 for L though, right?
I'm not plugging in 0 for L. I'm saying that at the point x equals L, the function has the value 0.
Gotcha.
We're
Okay.
plugging in L for X. Nice work, David. You were explaining something without telling him an answer. That was brilliant. Future teacher. Nice work.
Thanks.
So let me just say, I want to just say one thing. I'm concerned that I didn't make this clear to one of you in the breakout room. And then also I just kind of want to make sure everybody's on the same page here. But since you really started with EI, and I'm going to write it this way, Y double prime equals, what do we say? WL. Conceptually, does it make sense that you could just ignore the EI for now because it's a constant, pretend it's not there? I think most of you have got to here now. So I want to because this is the conversation I've had with everybody in the breakout room, and because I want to be able to let you guys go. So the first thing you're going to do is take the integral of both sides. And so what I'm going to do is I'm not ignoring the EI. I'm just saying, let's just leave it over there and just kind of ignore it for now. In other words, I'll take the integral of both sides. And so the EI is still there. If you take the integral of the right side, does it make sense you just got rid of one of the derivatives? So now there's a y prime over there. But let's see, I'm going to pick on people that weren't in the chat room yet. Hannah, what's the integral of this term? It's okay to be wrong, but you're going to answer this whether I help you or not. What's the integral
Okay.
of 5x?
Of
you know.
5x.
Well, I'm just saying WL over 2 is like a number. Like, don't, it's not confusing. That's just a number
Oh.
times it. Go ahead.
X squared times 1/4.
Yeah, that's exactly right. In other words, it's x squared over 2, but there's already a 2 over there. You guys all agree with Hannah? She's right. Let's see. This is over there. Evold, are you there, Evold?
Yeah, I'm here.
Sweet. So what's the integral of W over 2x squared?
Let's see. So it's W over 6x cubed.
I'm writing down what he said. Is he right or is he not right?
Wait.
Third domain.
It's right.
Should be right.
He's right. Nice job. Like, that's not terrible, except for, what am I missing? Everybody?
Oh,
Constant.
What's a constant? Again, that's essential in this problem. If you miss that, you're not even gonna come close to designing a beam. Like, that's essential here. Okay, that was easy. We just took the integral both sides. Let's do it again. I'm gonna pick on other people. The EI is still over here just hanging out. Jerry, are you there? What's the integral of WL over 4x squared?
Is it I'm not sure.
Tell me just the integral of x squared.
Is it 2x?
No, you're
No,
thinking
not two.
derivative.
Yeah.
Yeah.
Take your time.
Um,
I don't care.
X cubed.
X cubed. What else? What do you have to do with that 3?
It's the opposite of what you just did, but with
I can't function right now, honestly. I'm not sure.
Somebody help him. What do you do with the 3?
Divide by 3.
Divide it.
Divide by
Oh,
it.
okay.
Like a second ago, you multiplied by the 2 for a derivative. Well, in an integral, which is
Mhm.
going backwards, you got to divide. And then there was the WL over 4 there, right? So
So then
now
you
it
just
becomes-
do WL over 12x cubed.
Exactly.
That's all.
Beautiful. So in the same way, looks like there's who's still here. There we go. Drake, you willing to do the next one?
Is it going to be W over 24 times X to the 4th?
Rest of you agree with him, disagree with him?
Seems good to me.
Nailed it. What happened to the C though?
Well,
We have to
C
add
times
the
X
X
now.
value. Yeah.
It grew an X, right? Is this correct? We got it?
Well,
Need
What's-
another C.
You need another C. So if that C had been, you know, like an 8, then wouldn't this be 8X? But doesn't it also grow yet another C? Are those the same C?
Nope.
They're not. Like, that wasn't terrible. And I think maybe a decent chunk of you got to that place. Notice now the EI is still over there, but the key is really this. Does it make sense every one of these is divided by EI, not just the first 2? Some of you in the kind of when I talked in the chat said, oh, I don't want that EI over there. And so you divided it over here from the very start, which is totally fine. And then you took the integral as we did, but then you grew like a CX and a C, but those should be divided by EI as well. You see what I'm saying? So you're a failure of you failed to distribute. That's the only algebra mistake people make, and they make it their entire math career. Like, distributed law is like actually pretty hard. So you could think of it as this. I'll write this down. You could think of it as now remember, EI is just a constant. Do you all understand that when X equals 0, Y also needs to be 0? Do you all understand? This is what David was helping everybody understand. Do you understand when you get to the other side of the beam, you also have no deflection? Remember, how far is Y down? It's no down at X is 0, and it's no down at the other side of the beam when L is 0 as well. You've got to come up with C1 and C2 so that that's a true statement. C1 and C2 are not going to be like 5 and 7. They're going to be, well, look at your other constants. You got E's and I's and W's and L's. Those C1 and C2s are going to be like, WL over 6 or WL squared over E, or they're not just going to be 7 and 2. They're still constants, but in order for this to be true, in order for X equals 0, Y to be 0, and X equals L, Y to also be 0. In order for that to be true, you're going to have to find C1 and C2. When you do, you now own how beams work. You have an equation now that will do that. So again, you don't have to leave, but we're at the end of class and want you to be able to. So I want you to find Y equals X, and just note that C1 and C2 will have W's and L's and E's. It's like they're not just going to be 7 and 2. Secondly, I want to show you something rather amazing. I'm going to try this just totally live. I'm going to show you how to check your work. Let's see. Stop sharing. Sharing screen share. Google. Are you seeing Google right now? You're seeing me, you're searching,
Yeah.
right? So
See Google.
I need the deflection. Whoa, get your hands on home. Get your hands on home position. Deflection beam formula. Notice there's one down there that says beam deflection formula simply supported. I'm going to Google search that. There it is. I need it to be big. How do I make it bigger? How do I make it bigger? Is it Control plus? Yes. Let me find one of them. There it is. See right here? You're all seeing my hand on it, right? See what it says? 5WL to the 4th. Write this down. 5, this is the formula this is the simple algebra formula that people use for this, and you're creating it right now. It's 5WL to the 4th over 384 EI. Notice, what is that called though? What does it say over on the other side? Kind of a weird symbol.
Max change in weight.
It's Y max, like it's change max, but it's Y max. Where did we say Y max was? Where is the maximum Y? What location? In the center, which would be when X is what?
1/2.
Half of what?
L.
L.
Oh, dang. Oh.
Half of L. Now,
So this is the
again,
value.
Google search this yourself. That's a ridiculously simple algebra equation. Stop share. Screen share iPad.
So is that what we're supposed to get at the maximum, or minimum, I mean, of the curve? Like, is that the value? If we plug in L over 2, we should get that?
Correct.
X to three.
So I'm gonna write out what David just said as soon as my screen shares. with you.
W over
This is just like I'm getting chills down my. So
4.
there's two things I want you to calculate. One of them is this cool equation, y as a function of x with all the w's, e's, i's, and l's. But then I also want you to find y max, which is the same as y of L over 2. If you go to half of the way across the beam, and this is what's interesting about this is you will not find the equation that we're trying to make online. You'll find y max because nobody actually cares what the deflection is 5 feet in. They care what the biggest deflection is because that's what determines whether the beam is okay or not. We just saw that the answer to that was 5WL to the 4th over 384 EI. So in other words, if you go back to your equation that you think you got up here, hey, I think I got this right. If you put L over 2 in for X, it better pop out as 5WL to the 4th over 384 EI, or apparently you haven't figured this out yet. And what I would like and I've given hints to the smartest people in this class. So you're going to need hints, but I'd like everybody to get this under their own power. And when I say own, I mean with discussions with each other, discussions with me. I would like you to, what I like to describe is own this formula. I want you to own this formula, not borrow it. We just borrowed it off Google, right? That's cool. No problem with that. Notice what this is saying is the deflection at L over 2, I guess I'm rewriting the same thing, is equal to that. Do you see that as a ridiculously simple algebra formula? In other words, if I told you W is 100 pounds per lineal foot, the length is 20 feet long. These numbers don't make sense, but I'm just sticking them in right now. Does it make sense if you plugged all of those into that, you'd have the deflection, the maximum deflection? Like that's an algebra 1 problem to use that formula, right? It's an algebra 1 problem to use that formula. You have to be kind of like a genius to be the one that made that formula. I want you all to be that genius. I want you to be like, oh my God, I made that myself. You should. When I first saw this formula, I thought the 5 and the 384 were like approximations of some decimal. I thought somebody went out there with like a board and they put weight on it and they measured the deflection and they put a different weight on it and measured deflection. And then they did like regression and they went, well, this is pretty close. Let's use that formula. I didn't realize it was like made, literally built from nothing. And I want you to, kind of enjoy that power, that mental power, that you'll never be able to share with anybody. You try to share this with someone, they're going to leave you as fast as they can. And even if they liked it, they probably wouldn't be able to understand what you're saying because this is like hard. You got to be as smart as you guys are. You have to have taken a lot of math to even understand the explanation.
That's every dinner conversation I've had for the last couple of weeks.
Right. Where's the door? So that's the two things I want is for you to kind of go back. What you're going to turn into me is go back and don't have ugly work. Like you should be able to write this in one page, like where you just kind of show, hey, here's the y of x equation. And then I plugged in L over 2 and look, I got 5WL to the 4th over 384 EI. You don't get to quit on this unless you get 5WL to the 4th over 384 EI. I will give you 900 hints until you get there. You fail this, you can't pass this class. You can get an A on every test. And if you don't get 5WL to the 4th over 384 EI, you fail. Like you don't get to pass. Like this is too cool. I'll help you 900 times, but like you have to get this. This is just too cool. Which means you're going to get an A on this project.
Doug, after today's class, I think you should start like a TV show, kind of like Hell's Kitchen, except like Hell's Engineering, where it's like your fridge moves, you fail. It's like your fridge fails. Get out of my kitchen. Get out of my laboratory.
I will tell you what my dream for this is like, okay, now you know all this. Let's go make a bridge over a creek, and now you got to walk across it. And it's like 10 feet down to the creek, and so we're gonna video you going over.
I'll walk across Landing Bridge on mine.
You fall. So, feel free to bail if you need to bail or whatever, but I'm more than happy to stay here and just keep talking for another hour till everybody's like, okay, I'm leaving. So tell me if you want to go back to the chat room one-on-one.
I'd love to check my answer before I go. That's okay.
Yep. See you in the chat room. Breakout room.
I feel better about this because I made some fatal errors the first time. So we have our last.
You're smart. And if I'm teaching you something, that means I'm actually adding value to your life. So good.
Absolutely. I like problems like this. I like deriving things. It's a lot of fun.
I totally agree. It's so awesome.
That's what I got for just the general, like the particular solution.
You are ridiculously close, but if you put in X is L, you don't get 0.
You don't?
Try it. Do it live.
Yeah, the constant there is a little different than what I got.
Don't say it out loud just yet.
Yeah, I'm not going to. I'm not sure if
But-
mine's right either because the math later on isn't working out. So
Oh, wait. Does it need to be? I guess you're right. I guess I need to make this 24. Okay. But this would be 12. I see what you mean.
Yeah. Which
So
was
that
just
needs-
that was just a simple mistake on your part someplace, right?
I probably just skipped something, I guess, or just did it in my head.
So that 12 needs to be, now that still doesn't mean you're right necessarily, Landon. If that 12 on the top is a 24, is that what you got, or did you get something different?
I dropped a sign.
So you had the same numbers, but then not the same sign. Is that true?
Yeah, I had the positive constant there because I just completely algebra derped.
Mm-hmm.
Yeah.
Nice work. You guys are both there.
Whew, all right.
I had a question, Doug. I sent you my homework 3 late because I forgot to turn it in. I emailed it to you. Did you get that?
I did actually. I haven't. I've been a little chaotic, but I saw that email. So yeah.
I just wanted to make sure you got it because I did it like, I don't know. I just forgot to turn it in.
Yeah. In your case, David, I would be like, hey, I already emailed you the answers. You can't give me that, but you've already proven yourself to care and be bothered and love math, and so. And you've also
Thank you.
proven
I
your character
appreciate
to me, so I'm gonna give you credit for that.
I was done I'm totally done on time. I just, I don't know. I slipped my mind. So
Yeah. And on top of that,
you know what? I saved it to my computer and then I never turned it. Anyway. Okay, cool. So I'll just rework that and try to get the constant right. And when I write it up, it'll probably become clear. So, all right. Thanks, Doug. See you later.
Excellent job. You have a
Those
separate
forced
question, Landon?
mechanical vibrations are tough.
Oh, yeah. Yeah. I'm
That
excited to teach
I
you
was
guys
going to
that
read
tomorrow.
the chapter and oh my goodness, they just so complicated.
Yeah. So
Anyway.
I'll make it totally clear
All right.
tomorrow. I can explain it way simpler than the book does.
I sure hope so because those are a lot of constants.
It's a nasty business.
All right. See you later.
See you later.
Okay.
Do you have a
so I
separate
got-
question, Landon?
I actually have a separate question. So this is like more last week stuff, but when we're looking at with the like final note sheet we have for the kind of undetermined coefficient methods. I noticed that I've been doing a little bit of reading on like other sources, and a lot of them aren't just using a form; they're just finding it every single time.
Right. Yeah.
Is that a viable option for most of these, or does it get too ugly to
Yeah,
reasonably do?
they're usually super ugly. In other words, if you actually want somebody to fully solve it for those coefficients, you have to be really careful to keep it easy. Again, I find myself thinking that would be worth doing if we're doing what we did today, which is like making all the beams in the world work. Okay, well, if that's hard and it takes me a couple of days, then so be it, because now I could build a bridge. But if it's just kind of a random book problem to say, well, hey, this is the form of the guess, and then let's not worry about all the algebra that I've learned before this. Let's not worry about taking the time to actually determine all 6 of those coefficients. And that problem I did in class is a good representation of that, because man, that was really terrible. So yeah, the last 2 problems on that assignment are just like write the form of the answer, but let's not go figure out what those coefficients actually are.
And then I guess it's just kind of curiosity here, but do the units actually work out from a math perspective for this one? Because I know
Yes.
that okay.
Yeah.
Modules elasticity is like force per unit area, and then
Yeah.
moment of inertia is like
Let's go back. I
length
want to
of
tell
foot,
I want to tell that to
Okay,
everybody.
yeah, yeah.
That's really cool. I'm going to show you that. And I'll just tell people that don't want to know to not listen.
Mhm.
So don't listen to this if you don't want to. Well, actually, maybe who else has questions? Landon asked a good question about units. Like, do the units work out? I'm going to answer that before we leave, but I want to answer your individual questions first. So Hannah, you ready to head over there? I saw your hand. Okay, that's
Yeah.
good. So go share a white screen and then scratch like a first grader. Show me what you have.
Oh, like this? Oh,
Yeah,
wait.
green share screen. There you go. You got it. Now you can
Am I
write. with-
doing it?
Yep.
Okay.
See that.
So right now I'm to the point, well, actually I plugged in that L/2 to check my equation, but the problem is I got the right denominator, but I didn't get a 5 in the numerator. So something's off, I think, with my initial equation.
Yeah. So show me your initial equation.
Okay, so my initial equation right now is I plugged in, well, let me backtrack a second. For y of L equals 0, does that mean we're plugging in L for x in that equation? Okay, then I'm
Mhm.
so I have y equals let's see, WL over, wait, WL to the 4th.
That's after you plugged L in, right? Or plugged L into X. Like, give it to me before you plugged anything in, so I can see your original equation.
So before yeah, definitely. So my original equation was WL over 12 E I, and then X to the 3rd.
Correct so far.
Minus W over 24 EI.
Mm-hmm.
This is hard to write on. Okay, EI.
It's okay if it's
and
ugly.
then,
I'm tracking with you.
okay, and then X to the 4th. Oh,
Beautiful.
that's a 4.
Yep, totally.
Plus CX over EI. And then one of our initial conditions was y of 0 equals 0, right?
Mm-hmm.
So then that C2, that last constant, turns into a 0 after plugging that all in. Okay. So from there, I plugged in L for X, and I got, like, oversimplified, obviously. I got WL to the 4th because L times L to the 4th over 12 EI. And then, well, before I write this out, then I got minus WL to the 4th over 24 EI.
Right.
But those can be combined to
Right.
get WL to the 4th over 24 EI.
You're
right?
right. Yeah.
Okay, so this is where I think I went wrong, because
So
then
go
my
ahead and
final,
erase that 12 and write a 24 there.
okay,
just
Make
because you're
that
right.
easier.
And then you still have the plus CL over EI, right?
Right. So that's what I have left is that CL over EI. And is
And
that
what's Y equal to though? When X is in,
Y is equal to 0?
right? So get rid of that Y and put a 0 over there.
Okay, so 0. But where do we go from here then?
Now solve for C. You got it. Solve for
Oh,
C.
because everything else is constants.
Yeah, that's right.
Oh, and then, okay, so then once we have that C value, then probably everything will come together so that I actually get that 5W L to the 4th over 384 EI.
Yeah.
That's wonderful. That helps out so much. Okay.
And isn't it a trip? Because it's like if you don't get the initial conditions, like the initial conditions are everything here. The integral of C is CX. Like if you don't tackle all that,
Yeah.
like you don't get to model a beam. So yeah.
It's
So
super cool though.
oh man, isn't it so cool?
It's when I got the 384 EI on the denominator, I was like, yes, this is
Yeah.
awesome. But I was just off by the C value. So I just need to
Wait
do
till
that.
you get the 5, man. You're probably gonna scream.
I'm gonna be so excited. Okay,
You're
I'll
there. You're totally there.
yeah, I was so close. I was like, okay, this is good. Well, thank you.
Yeah. Okay, we're going back.
Perfect.